Universe. By its very existence, it asks us bulks of questions. Where did it come from? Why? What is its purpose? Nobody knows the exact answers. However, this does not mean that no one is trying to find them. Science is looking for these answers. And one of the main instruments to unlock the mysteries of our vast universe is the James Webb Telescope. This July marked the first full year of science operations for James Webb, which only began taking science data halfway through 2022. With hundreds of image releases and thousands of scientific papers that have already come from humanity's latest flagship astrophysics observatory, the telescope has been our cosmic workhorse, revealing the universe in a whole new light with unprecedented resolution and wavelength coverage to view the cosmos. But despite providing new insights into galaxy formation and the evolution of our universe, the premier observatory has raised some concerns that the history of the early universe needs to be rewritten. Join us as we dig deep into how James Webb just upended cosmology. Until around a few 100 million years or so after the Big Bang, the universe was a very dark place. There were no stars, and there were no galaxies. After the Big Bang, the universe was like a hot soup of particles. When the universe started cooling, the protons and neutrons began combining into ionized atoms of hydrogen and deuterium. Deuterium further fused into helium-4. These ionized atoms of hydrogen and helium attracted electrons, turning them into neutral atoms. Ultimately, the composition of the universe at this point was 3 times more hydrogen than helium, with just trace amounts of other light elements. This process of particles pairing up is called recombination, and it occurred approximately 240,000 to 300,000 years after the Big Bang. The universe went from being opaque to transparent at this point. Light had formerly been stopped from traveling freely because it would frequently scatter off the free electrons. Now that the free electrons were bound to protons, light was no longer being impeded. The era of recombination is the earliest point in our cosmic history to which we can look back with any form of light. This is what we see as the cosmic microwave background today, with satellites like the Cosmic Microwave Background Explorer and the Wilkinson Microwave Anisotropy Probe. Following this are the cosmic dark ages, a period of time after the universe became transparent, but before the first stars formed. When the first stars formed, it ended the dark ages and started the next epoch in our universe. Another change occurred after the first stars started to form. Theory predicts that the first stars were 30 to 300 times as massive as our sun and millions of times as bright, burning for only a few million years before exploding as supernovae. The energetic ultraviolet light from these first stars was capable of splitting hydrogen atoms back into electrons and protons or ionizing them. This era, from the end of the Dark Ages to when the universe was around 1 billion years old, is known as the epoch of reionization. It refers to the point when most of the neutral hydrogen was reionized by the increasing radiation from the first massive stars. Reionization is an important phenomenon in our universe's history, as it presents one of the few means by which we can indirectly study these earliest stars. But scientists do not know exactly when the first stars formed and when this reionization process started to occur. The emergence of these first stars marks the end of the Dark Ages in cosmic history, a period characterized by the absence of discrete sources of light. Understanding these first sources is critical, since they greatly influence the formation of later objects such as galaxies. The first sources of light act as seeds for the later formation of larger objects. But exactly what the universe's first light, that is stars that fused the existing hydrogen atoms into more helium, looked like, and exactly when these first stars formed, is not known. These are some of the questions Webb was designed to help us to answer. Imagine light leaving the first stars and galaxies nearly 13.6 billion years ago and traveling through space and time to reach our telescopes. We're essentially seeing these objects as they were when the light first left them 13.6 billion years ago. By the time this light reaches us, its color or wavelength has been shifted towards the red, something we call a redshift. Why? In this particular case, it's because when we talk about very distant objects, Einstein's general relativity comes into play. It tells us that the expansion of the universe means it is the space between objects that actually stretches, causing objects, galaxies, to move away from each other. Furthermore, any light in that space will also stretch, shifting that light's wavelength to longer wavelengths. This can make distant objects very dim or invisible at visible wavelengths of light, because that light reaches us as infrared light. Redshift means that light that is emitted by these first stars and galaxies as visible or ultraviolet light actually gets shifted to redder wavelengths by the time we see it here and now. For very high redshifts, for instance, the farthest objects from us, that visible light is generally shifted into the near and mid-infrared part of the electromagnetic spectrum. For that reason, to see the first stars and galaxies, we need a powerful near and mid-infrared telescope, which is exactly what Webb is. Before James Webb's debut, its predecessor, the Hubble Space Telescope, held the record for the earliest galaxy ever found. We can see that object, called GNZ11, as it was about 13.4 billion years ago, around 400 million years after the Big Bang. However, once James Webb turned its gaze on the universe, it repeatedly smashed Hubble's record. As of mid-2024, all 10 of the top 10 most distant objects were discovered and measured with James Webb, surpassing Hubble's old limits by large amounts, 17. And our most distant object known to date is the galaxy Jade's GS Z14-0, which was discovered and measured in a deep field view of the distant universe, using the James Webb's NIRCam and NIRSpec instruments. It has a remarkable set of properties. It comes to us from when the universe was just 285 to 290 million years old, or just 2.1% of its present age. It's bright, as in 4 to 5 times brighter than all the other bright galaxies found from the universe's first 400 million years so far. It's relatively large already, spanning an estimated spatial extent of around 1,700 light-years, and it's presently a whopping 33.8 billion light-years away, the most distant individual object ever discovered. But while James Webb is truly revealing the universe as we've only dreamed of seeing it, rife with tremendous advances and surprises, it's also raising big questions about the early universe. The trouble began almost as soon as James Webb first peered into the distant universe. When this telescope peers at the most distant cosmos, it sees things as they were shortly after the Big Bang. James Webb's first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies, far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. The scorching conditions in the first few 100,000 years after the Big Bang meant that matter couldn't settle down and condense into entities, such as stars and galaxies. As the universe expanded and cooled, standard cosmological theory holds that particles of dark matter, mysterious stuff that outweighs normal matter 6 to 1, clumped under the force of gravity and formed massive halos. These then gravitationally attracted regular matter, which slowly accumulated in the halos and produced the stars and galaxies we see today. Most models estimate that a galaxy the size of our Milky Way wouldn't form until roughly 1 billion to 2 billion years after the Big Bang. But in that first James Webb image of the SMACS 0723 cluster, astrophysicist Erica June Nelson of the University of Colorado Boulder noticed these big, honking red disks that appeared to be extremely massive galaxies rapidly forming stars. These dusty, red, elongated galaxies, 6 of them, all seem to have existed within the first 500 million to 700 million years of cosmic history. Based on the object's brightness, Nelson's team calculated that they might each weigh at least 10 billion times the Sun's mass. One, in particular, was a colossus containing perhaps 100 billion suns, on par with our own galaxy, and could have 2 nearby companions, suggesting that it was part of a galactic group. And in the words of Michael Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin, their quoted properties are so massive that it's really hard to see how you can form those and keep our current models of cosmology completely intact. Most in the field acknowledge of cosmology that their understanding of galaxy formation will likely have to shift to account for James Webb observations. But will it be a minor adjustment or a more radical alteration? Among the simpler possibilities is that the earliest stars and galaxies came together more efficiently than researchers currently believe. It could be that the primordial universe was much denser and more compact than researchers think, perhaps allowing gas and dust to collapse especially quickly into stars. In other words, maybe in the very earliest systems, it's all kind of going gangbusters, and there's nothing to stop it. This would allow for the creation of larger numbers of galaxies that are heavier much earlier in cosmic history than existing theories suggest. But the efficiency of galaxy formation would likely have to be much higher than current models assume. A more exotic explanation tweaks conceptions of dark energy, which is generally believed to be causing the observed accelerated expansion of the universe. Physicists consider the density of dark energy to have been a constant since the Big Bang, but discrepant measurements of the cosmos's expansion might require a rethink of the nature of dark energy. Studies of the nearby universe suggest a faster expansion rate than the rate extrapolated from observations of the infant universe. Several models that have been around since before James Webb launched, called early dark energy, posit that more dark energy existed roughly 50,000 years after the Big Bang. Such models, which help resolve the expansion rate discrepancy, also happen to predict that galaxies grew faster and more abundantly in the early universe, which could explain James Webb's sightings. But there's an obvious problem. The standard model of cosmology, with its constant dark energy density, has been extremely successful in explaining the evolution of the large-scale structure of the universe, comprising the observed web of galaxies, galactic clusters, and clusters of clusters. Any changes to that model will need to retain such positive aspects while addressing the new observations. Most researchers are taking a wait-and-see approach before abandoning long-standing ideas in favor of some new view of the cosmos. But the latest discoveries of James Webb, once again, called the whole picture of early galaxy formation into question. James Webb's far-sighted scrutiny has unveiled the existence of an enigmatic population of galaxies in the early universe previously unknown to astronomers. These galaxies are fainter and farther than ever before, and somewhat surprisingly, many of them are redder and more compact than anyone expected. These little red dots have stirred the imaginations of astronomers worldwide, as they may have major implications for our understanding of cosmic evolution. But to date, their exact nature and what exactly they're telling us about the early universe remains uncertain. However, some things are clear. Most of the little red dots blazed during a relatively short period lasting 1 billion years and starting about 600 million years after the Big Bang. In a tantalizing mystery, outside of their ancient relic light Pick It Up by James Webb, there seems to be no trace of them in today's universe. Why did they vanish? Or what did they morph into? Their sudden disappearance is a profound enigma. Their distinctive redness isn't merely a matter of red shifting. Rather, it indicates they were emitting large amounts of light at longer, redder wavelengths. Whether this is from an intrinsically red galaxy, or instead from large amounts of dust that can redden light, is unknown. Their compactness is also disconcerting. A typical little red dots has an approximate radius of no more than 500 light-years, while for some of them, it can be smaller than 150 light-years. Our own Milky Way galaxy in the modern-day local universe is more than 100 times bigger. This is about all we know. The road before us now forks off in at least two branches. Little red dots are either galaxies hosting a central supermassive black hole, or they are galaxies hosting a vast number of stars in a small volume. Each interpretation has problems. First, clues strongly suggest that, similar to all large galaxies we see in our local universe, these little red dots from the early universe harbor a central supermassive black hole, one between a few million and a few 100 million times the mass of our Sun. We can ascertain them by their spectra, the rainbow-like chart of individual wavelengths or colors of light they emit. Black holes themselves don't emit light, but matter falling into them releases copious amounts of radiation, powerfully shining to help detail its demise. Astronomical spectra can indicate how fast gas is racing around a black hole, fighting its immense gravitational field, and effectively allowing the black hole to be weighed. This signature, the broadening of some features in the spectra, is present in most of the little red dots, indicating gas velocities of thousands of kilometers per second, just as would be expected for material spiraling to its doom near a supermassive black hole. However, the black hole hypothesis is also marked by something bizarre. A significant fraction of the light produced by material falling into a black hole comes in the form of X-rays. The little red dots should thus be visible to X-ray telescopes if they contain supermassive black holes. In one of the most puzzling plot twists of modern astronomy, they are not. Most of the little red dots discovered so far show no sign of X-ray emission. And the oddities keep coming. In the nearby universe, profound correlations, or scaling relations, exist between the mass of a central black hole and the number of stars in its host galaxy. Typically, such a black hole's bulk is about 0.1% of the total mass of its galaxy's stars, a clue that these two profoundly different astronomical objects somehow co-evolved. If the little red dots contain supermassive black holes, these would seem much more massive than what that well-known scaling relation would dictate, weighing in at up to a mind-boggling 40% of the stellar mass of their entire galaxy. This peculiarity could be crucial evidence for establishing how the first black holes formed at even earlier cosmic epochs, scarcely plumbed even by James Webb. But what if the little red dots contain only stars? Black holes feasting on matter are generally much more efficient than stars at producing light. Hence, for stars alone to make the amount of light observed from these galaxies, vast numbers are required. Imagine squeezing a Milky Way's worth of stars into a volume with a radius 100 times smaller than our familiar home spiral galaxy. If we placed a sphere centered on our Sun and with a radius of 4.24 light-years, it would contain only another star, Proxima Centauri. The same sphere placed in one of these little red dots would contain, on average, more than 1 million stars. The song, "A Sky Full of Stars," would acquire an entirely new meaning there. What then are these mysterious apparitions so near the break of cosmic dawn? The truth is, we do not know yet. Future investigations with James Webb, especially at longer wavelengths in the infrared, to probe the emission of dusty structures around central supermassive black holes, may help. Furthermore, deeper X-ray observations, also with next-generation, high-resolution X-ray observatories, such as the proposed AXIS, will hopefully detect high-energy photons from the little red dots. Much like Picasso's mysterious gentleman with a bow tie, these enigmatic objects seem to inhabit an alternate reality, one that tells a story from an unexplored chapter of cosmic history. With time, astronomers will reconcile them with our current understanding of the machinery of the universe. However, for the moment, we keep wondering, awestruck and searching for answers. In another outstanding observation, the James Webb Space Telescope has discovered what could be the earliest star clusters in the universe. Under Webb's view, the 5 proto-globular clusters, swarms of millions of stars bound together by gravity, has just spotted inside the cosmic gems arc, a galaxy that formed just 460 million years after the Big Bang. The cosmic gems arc gets its name from its appearance. When seen from our solar system, the star-studded galaxy looks like a hair-thin crescent due to the powerful gravitational influence of a foreground galaxy, which magnifies and distorts the distant galaxy's appearance. The galaxy is the most highly magnified region seen in the first 500 million years of our universe, giving astronomers an unprecedented window into how the stirrings of the first stars sculpted galaxies during cosmic dawn. Cosmic dawn is the time encompassing the first billion years of the universe. Roughly 400 million years after the Big Bang, the epoch of ionization began, in which light from nascent stars stripped hydrogen of their electrons, leading to a fundamental reshaping of galaxy structures. In the words of study first author Angela Adamo, an astronomer at Stockholm University, the early universe is nothing like we expected. Galaxies are more luminous, they form stars at breakneck speed, and they do so in massive and dense star clusters. We are building a new understanding of how early galaxies formed. The researchers published their findings in the journal Nature. As stars form, they fling out material in the form of winds and jets of ionized plasma, a process known as stellar feedback. According to Adamo, to form these 5 star clusters, this tiny galaxy had to do so with very high efficiency. The stellar feedback from the stars and star clusters must have been tremendous. Scientists discovered the cosmic gems arc in 2018 using the Hubble Space Telescope. Usually, galaxies from such an early time emit light that is far too faint to be detected by telescopes. But a phenomenon called gravitational lensing can help astronomers view them. As Einstein outlined in his theory of general relativity, gravity is the curving and distortion of space-time in the presence of matter and energy. This curved space, in turn, sets the rules for how energy and matter move. This means that even though light travels in a straight line, light can be bent and magnified by the presence of gravity. In this case, the galaxy SPT CL J06155746 sits between the cosmic gems arc and our solar system, bending and magnifying the early galaxy's light so it can be viewed by telescopes. By pointing James Webb at this region of curved space, astronomers observed the cosmic gems arc in unprecedented detail, resolving the 5 globular clusters nestled within. They found that the clusters were incredibly dense, being roughly 3 orders of magnitude denser than star-forming regions observed closer to Earth. The clusters are among the first to ever be observed. But it's still unclear whether they are the first to exist. To learn more about the cosmos's first embers in the region, the researchers will follow up with a spectroscopic analysis using the Webb telescope. This will enable astronomers to reconstruct the physical properties of the clusters, further constrain their ages, and trace the impact the cluster's stars had on their wider galaxy. In addition, a new composite image combines data from both James Webb and the Chandra X-ray Observatory to reveal more about the dense neutron star at the center of one of the brightest supernova remnants in the night sky. The latest data shows that the nebula's neutron star, the leftovers of the X star's core, is dramatically changing over time. The neutron star inside the Crab Nebula is what astronomers call a pulsar because it rotates around 30 times per second, sending out a beam of radiation on every rotation, a bit like a lighthouse. Chandra captured repeated observations of that radiation, enough to show that the neutron star's energy has produced a shock wave. According to NASA, this high-speed wind of matter and antimatter particles is moving through the vast nebula, which measures 11 light-years across. That shock wave is the ring you see in the image, while jets of X-ray emitting particles coming from the pulsar's poles are also visible. Chandra's data has also been used to create a time-lapse movie of the Crab Nebula's ring and X-ray jets. Collected over 22 years until 2022, the data reveals the X-ray jet's whip-like movement. Astronomers are not stopping here. They plan to gather more data on the pulsar later this year, hoping to uncover further changes. A remarkable finding. Astronomers have discovered 2 new satellite galaxies of the Milky Way, and these findings could help us better understand dark matter, the mysterious stuff that accounts for around 85% of the matter in the universe, yet remains effectively invisible to us. The discoveries also move scientists a step closer to solving a lingering problem with the Standard Model of Cosmology, or the Lambda Cold Matter Model, also known as LCDM, in which the word cold assumes dark matter is composed of particles moving slower than the speed of light. The newly found small gatherings of stars have been designated Sextans II and Virgo III. They join the around 60 known dwarf galaxies that swarm around our much larger home spiral galaxy at maximum distances of 1.4 million light-years. The most famous and largest of these dwarf galaxy satellites of the Milky Way are the Large Magellanic Cloud and the Small Magellanic Cloud. How many satellite galaxies does the Milky Way have? This has been an important question for astronomers for decades. Team leader Masahi Chiba, a professor at Tohoku University, said in a statement. Many tiny dwarf galaxy satellites of the Milky Way remain undiscovered due to their distant and faint nature. But Chiba and colleagues were determined to start finding these elusive objects. So, they turned to the Subaru telescope. This powerful ground telescope, located near the summit of Mauna Kea, Hawaii, is well suited to hunting dwarf galaxies, and the same team had previously used it to detect 3 new satellites of the Milky Way. Dark matter is a lingering cosmological problem because it neither interacts with light nor the ordinary matter that composes stars, planets, moons, and us. And, well, if it does interact with those things, those interactions are far too weak for us to notice. That means dark matter could be composed of particles that are currently undiscovered, though there are potential explanations that don't require extensions to particle physics. For instance, scientists have explored the idea that dark matter could be made of tiny primordial black holes left over from just after the Big Bang. However, dark matter indeed interacts with gravity, which can influence the motion and dynamics of light and everyday matter. This has allowed scientists to infer the presence of dark matter and eventually determine that large galaxies are surrounded by vast halos of this mysterious substance. Those halos, it's believed, extend far beyond galactic disks and halos of visible matter. The LCDM predicts that these dark matter halos have played a significant role in the evolution of galaxies. In the early universe, they formed gravitational wells into which the gas and dust that formed stars within galaxies were drawn. Eventually, these halos also drew together, forming large galaxies like the Milky Way. This model also suggests there should really be hundreds of satellite galaxies around the Milky Way and other major galaxies. For instance, simulations using LCDM predict that our neighboring galaxy, Andromeda, should be surrounded by around 500 satellite galaxies. Yet, astronomers have seen just 39 dwarf galaxies swirling around Andromeda. For the Milky Way, some simulations based upon the Standard Model of Cosmology indicate that our galaxy should be orbited by about 220 dwarf galaxies. Yet, scientists can't figure out where they all are. The discovery of Sextans II and Virgo III helps to redress that balance. Still, results spinning out of these findings could present cosmologists with the opposite problem they were facing before this. Though the number of Milky Way galaxies identified is still well below the predicted 220 dwarf galaxies, the team behind this research took into account the fact that the Subaru can't see the entirety of the night sky over Earth. They combined the distribution of dwarf galaxies Subaru has been able to see with its night sky footprint to calculate an estimate for how many satellites should, in reality, surround our galaxy. This led to the calculation that 500 galaxies surround the Milky Way, over double the amount predicted by simulations based on the LCDM. So, have scientists gone from a not enough dwarf galaxies problem to a too many dwarf galaxies problem? Maybe not. Recently, amateur astronomer Giuseppe Donatiello discovered 5 new satellite galaxies around the Sculptor Galaxy, officially known as NGC 253. When he and a team of astronomers looked at the distribution of satellite galaxies around the Sculptor Galaxy, including 3 previously found by Donatiello himself, they found that the distribution of these galaxies, which sit around 11.5 million light-years away from Earth, was uneven. In other words, the tiny galaxies seemed to have a favored direction, with more galaxies lying to one side of the Sculptor Galaxy than the other. If there is also a favored direction to dwarf galaxies around the Milky Way and the Subaru telescope happen to be looking this way, then the estimates based on Subaru's observations would be inflated. The team behind these Milky Way dwarf galaxy findings now intends to further investigate the actual number of satellite galaxies surrounding us with yet another ground telescope. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.